Hey guys, welcome again. This is going to be another look at related rates. We talked about it this morning, but I have about 4 more problems I want to show you. I don't know. I might split it into 2 videos, one on 2 problems and the other on the last 2. We'll see. Anyway, I have put this list of how-tos in terms of related rates. So we're getting bombarded with this. There's a video on part 1. This is going to be part 2. And there's also the class meeting video that helps you understand this. So let's just look at the problems. A spotlight on the ground shines on a wall 20 meters away. If a man 2 meters tall walks away from the spotlight and straight towards the wall at a speed of 1.5 meters per second, how fast is the length of his shadow on the wall decreasing when he is 8 meters from the wall? So we got a ground, we got a wall, we got a light that's on the ground, and we got some guy that is standing in front of the light, walking towards the wall. Okay, so it's interesting to think about, as this person approaches the wall, and here's the light again, and if he's super close to the wall, still the same guy, right? You can notice that the shadow is actually decreasing. That's a lousy sketch because he's a little taller over here. But anyway, what's happening is if he walks towards the wall, his shadow will decrease. So what's the math behind this? How do we get a relationship here? All right, so let's start off with making this a clean sketch. This guy is 2 meters tall. The light is shining like so. And yes, it said it is 20 meters away. And yes, it said I used the 2, but also there's the speed at which he's walking in this direction. Okay, so there's 2 things that are changing here. His height is not changing. The shadow is changing. I'll put a variable there. And the distance he is from the wall or the distance he is from the light is changing. Your choice. I'll put the X right here. Okay, so now I have a picture like that. Let's see, maybe, well, I see that in my notes I did it differently, so how about I cheat and go, let X equal that. You can go either way with it. Okay, the whole thing is to try to get a relationship going between X and Y somehow. You know, as this guy's walking, he stays 2 meters tall. What's changing is the distance X from the spotlight to the man as he's walking. How do we get a relationship here? All right, I didn't write the 20. Where does the 20 go? Well, the 20 is this way, meters this way. Okay, cool. I think we have everything we need. Now here's what we do. We use similar triangles to make this thing work. Similar triangles means I've got a triangle. This is why Richard in the past put an X here to make this life easier. And then the larger triangle, this is Y and this is 20. So that the relationship we have between the 2 by similar triangles is, perhaps you can write X over 2 is equal to 20 over Y. Okay, there. That's the hard part. We have them related to each other. As the man walks towards the wall, X is changing, but then so is Y changing at the same time, at perhaps a different rate. Okay. And as he's getting closer to the wall, at first perhaps the shadow drops dramatically, but then it slows down. And in fact, it would head towards 2 because that's how tall he is when he reaches the wall. The next step is to, excuse me, find the related rates equation, which means to implicitly derive. I would probably go xy is equal to 40 to make my life a little bit easier, because now what we're going to do is derive implicitly. Okay, what we're looking at is a product rule. Okay, so we'll derive x, we call it dx dt. Leave y alone, plus leave x alone, dy dt is equal, derivative of 40 is 0. This is where we're at right now. All right, so related rate says we have got to find all the variables we need. Now what's changing? The problem asked for how fast is the length of the shadow decreasing as he walks towards the wall. Well, the length of the shadow is our variable y. So I bet we're looking for dy dt, and we'd expect it to be negative. Okay. All right. What we end up doing is we have to fill in all of these guys except for dy dt and solve for dy dt once we're done. Well, okay, let's ask some questions. What does dx dt stand for? The rate at which this distance is changing from the spotlight to the man. You know what that equates to? We're finally going to use this number. He's going 1.5 meters per second. He's heading towards the wall. X is actually stretching. As he walks farther and farther, X is actually growing at a rate of 1.5 meters per second. Well, what is Y at that moment? Well, that's a good question. And for that matter, what is X? Well, X we know, come back up here, when he is 8 meters from the wall? At that moment, how fast is the shadow changing? Well, that means that X is 8. He goes here. Y has to be figured out too. How do you figure out Y? Watch. You have to go back to this equation to figure out Y. So let's do that. We have X is 8 over 2 is equal to 20 over Y. Okay, so 8Y is equal to 40, and it looks like Y itself is 5. So it's exactly when the man is 8 meters, what did I say? I might have made a mistake here. Wait a second. From the wall, X is not 8. X is the distance from the light, so I made a mistake. Let's fix this thing. We need this measure right here from the wall. So we're going to erase all that, and we're going to correct this and say X is not 8. What is X really? Well, X is 8. No, we want X is whatever it is, but what this is this is 8. So if this is 20, this is 8, X must be 12. So X is equal to 12. I almost blew it. This is a 12. So that's how that goes. Got to watch your variables. But now we're going to find Y. So if X is 12 over 2 is equal to 20 over Y, we get 12Y is equal to 40. So Y is 40 over 12, which can reduce 10 over 3. Okay, 10 over 3. Finally. So what mistake did I make? I assumed that X, I didn't read the problem carefully enough. From the wall was important to us. Okay, so I was saying X is 8, but no, from the wall is 8 this way over here and not this X over here. Okay, well, we saved it. Anyway, we'll divide by 3. That's 0.5 times 10 plus 12 times dy dt. The rest is gravy. So this is 5 is equal to 0. 12 times dy dx is 0. And we're off to the races. What we're finding is that dy dx is a negative 5 over 12, which is a good answer. And we say minus 5/12 of a meter per second. Okay, good answer. I like it. That's that one. I'm going to do one more and then stop the recording, and that'll be it for this one. So you can look it over again and see how I messed it up. That's always a good thing to look at as well. We're never perfect in this industry. What else we have? I was going to do the ladder problem as well. It's the famous slipping ladder. So let's read it. Actually, I was saying it's your turn. You can try it, but you can, any one of these, read it, stop the recording, and then try it, and then see if we're in agreement. That's actually a good toy to do. If you feel confident, do it, and it's a good learning device. So either you've done it or you're not, but here we go. A 20-foot ladder is leaning against a building. Okay, there's the building. 20-foot ladder. We're going to write that that is 20 feet. Okay. And if the foot of the ladder is sliding away from the wall at a rate of 0.45 foot per second, so it's going in this direction. The foot is sliding 0.45 feet or foot per second, sliding it out. I always think of like old comedies in this black and white silent movies or whatever, the Buster Keaton sliding down or something. how fast is the top of the ladder sliding down? Because, you know, if you pull this way, this guy's going to come down this way, wouldn't it, of course? Sliding down precisely when the top of the ladder is 12 feet high. Well, what is changing? What are our variables? You can go, well, here's an x sitting right there. X is growing, the distance of the foot of the ladder from the wall, and this could be y. Y could be the top of the ladder down to the ground. So that makes sense. Those two are the variables that are changing. And in fact, the one that's changing that we're curious about is how fast is the top of the ladder sliding down the wall. So once again, we have a relationship. This time it's Pythagoras. We've got x squared plus y squared is 20 squared. Okay. Great. Let's implicitly derive. How about we go 2x times dx dt plus 2y times dy dt. Every time I'm deriving is 0 over there. Every time I derive, it's not, there's a third variable t, the parameter t if you want to call it, and it's always there. Okay, it's a chain rule. All right, so now we just want to plug and chug. We actually are trying to figure out dy dt. What is that? So that means we need to know y. There's a 2 there. We need to know dx dt. We need to know x. And if we have those guys, we're in good shape. Okay, so the rates are usually given. This guy right here, 0.45t, is the rate at which x is growing. X is growing, so that would be dx dt. So this is equal to dx dt. And I'm going to plunk that number in for dx dt, 0.45. Squeeze them in there. Okay. But the other two, I need x and I need y. These guys depend on the moment they're talking about, and they're talking about 12 feet high. The moment the top of the ladder is 12 feet high. Well, what that means to me is when y is 12. So we still need x, but we know that y is 12 here, okay? So to find x, we typically have to go back to this relationship, okay? So we would have to say x squared plus 12 squared is 20 squared, and I think what we get, x squared is equal to, gosh, I think it's a 3, 4, 5. This is the 3, this is the 4, this is the 5. I think that's right. Is that what I figured out? So I think I found x is 16 feet away. So 12, 16, 20. All right, so let's put that in, 16. And the rest is just solving. I mean, so for example, this turns out to be 14.4, and of course, plus 24 dy dt is equal to 0. The cool thing about it is you would expect it to be negative, that y is changing, and in fact, that's what you get. You get a negative value. In fact, for this one, I got minus 0.6 foot per second. That's the answer, okay? That's it. So I will stop the recording. And upload it for you guys.